Hi, my name is Elliot. I just finished my undergrad degree here at Northwestern, and I work in Todd Murphy's lab.
Hi, my name is Anastasia, and I'm a PhD student working at Todd Murphy's lab.
And today we're going to be talking about modeling biomechanical systems. Now in class, you've already learned how to model a variety of systems using common components such as springs, masses, and dampers. In an earlier demo, you also looked at how these components' constitutive relations influence a system's behavior. For certain types of biological systems, developing useful models and correct constitutive relations is very challenging. Nevertheless, today we're going to show how using the modeling tools you already know, we can look at systems such as rat whiskers, human muscles, and even how the body balances.
You will all know by now that if you want to analyze a system's behavior, then you have to have some kind of governing equations. In class, you've been doing some similar of these, but in general, you could have much more complicated equations. Yes, just like this, for example. But don't let this scare you. Yes, when you look at a system, it's not obvious what these equations are, but you can use familiar components to derive them, just like we'll try to show you for the rest of this demo. In general, keep in mind that no matter how simple or complex a system is, you will always end up representing it by a differential equation that you will want to solve to see how the system evolves in time. Now, Elliot is going to say some things about the rat whiskers.
So the first example of a biological system we're going to look at is rat whiskers. Rats use their whiskers to help them sense and explore their environment. As a rat taps and brushes its whiskers against an object, forces are generated at the bases of those whiskers. These mechanical force signals are then transmitted to neurological signals that are interpreted by the brain. By studying and correlating forces with neuron activity, we can begin to better understand how the rat's brain comprehends its environment. Now, a rat has about 30 whiskers on one side of its snout, and each whisker has a shape that's approximately parabolic, something like this. As the whisker contacts an object, it is going to deform in some way. Let's call this pink line the deformed configuration. The goal of a good model of the whisker would be to predict what this deformation is and what the forces are at the base of the whisker right here, because this is ultimately what the rat senses. In order to understand more about the rat whisker system, we need to build a model of it. And the way we do that is to discretize it. We break it down into a series of rigid links that are connected by these joints that have rotational degrees of freedom. Now, this model is good for two reasons. First of all, it's physically motivated. Experiments have shown that the rat whisker is very stiff in the axial direction, or in this direction, but is much less stiff in the transverse direction right here. Second of all, it gives us a place to start with computationally. By choosing the number of links in the whisker, we can both control the amount of accuracy that we have, and we can also control how much computation is needed to compute a solution. Now, this system right here might not look like anything you've seen in lecture so far, but really it is. Let me draw this second system right below it. This you definitely have seen. This is just a series of point masses that are connected by springs and dampers. The analogy between these two systems is that here we're interested in linear displacements of the masses. Let's call them x1, x2, and so on. In the whisker system, we're concerned about rotational displacements at each of the joints. We can call those, for example, theta 1, theta 2, and so on. We can also build in spring and damping elements into the whisker by using what are called torsional springs and dampers. The symbol for a torsional spring is this little spiral right here. So for instance, in this system with the linear displacements, we might have a constitutive law for the springs that looks something like this. F sub s equals negative kx. For the whisker, we might have something like tau, which stands for torque, a rotational analog of force, equals negative k times theta. And we could determine this k right here based on geometry and also material properties that are determined experimentally. And likewise, we could also put damping elements into the whisker. Once we have our model, we can derive our equations of motion and simulate the dynamics. Here's a simulation of the rat whisking in free air and also of making contact with an object. The last point I'd like to make is that we need to give special consideration to what happens when there are contact forces. As I've drawn it here, I don't have any external forcing happening on the whiskers. But if contact is made with an object, we might have some external force that would cause a deformation. The magnitude and direction of this force is going to depend on the size and shape of the object, but you get the idea that we're going to need to model some aspects of the environment and not only the whisker itself. So we need to make a modeling choice of what we want not only in the system but also in the environment. And this modeling choice is often informed by what we want to learn about the system. This is an idea that Anastasia is going to expand on in the second part of this demo, where she talks about how you can model different aspects of the human body based on what you really want to learn.
Sometimes biological systems are just too complex to model completely. So what do we do then? We choose which aspect of the system we want to model, depending on what we want to learn about the system. Let's see how that works. Let's say that we want to model some dynamic behavior of the human body. Well, that looks much more complicated than modeling the whiskers. But you can think that the human body consists of muscles, and then you can take a step back and model just a single muscle. And if you have a model of a single muscle, then you can represent the human body as a combination of muscle models and derive the equations of motion. The most commonly used muscle model is the one introduced by Hill, and you will see that it consists from elements that you have already seen in class. Let's take a closer look at it. It consists of a spring in series with a parallel combination of a spring and a damper. The only component you might not be familiar with is the contractile element, and you can always think of it as an external force acting on the springs and the damper. Now, the springs here are nonlinear, which means that if we plotted the force with respect to the position, we would not get a nice-looking straight line. Remember that this is a biological system and not an engineered one, so we would expect these nonlinearities to come up one way or another. Now that we have the model of a single muscle, we care about the length of the muscle, and you can use the methods you have already learned in class to derive the differential equations that, if you solve them, they will tell you how the length of the muscle evolves in time depending on the external force. So now that we have the model of a single muscle, let's combine a bunch of them and see what happens. Let's say that we want to simulate a hand grasping objects, like here, for example. Here, each line represents a different muscle path, and it is modeled exactly as I showed you before. We're controlling the external force acting on the springs and the damper to make the hand move. Now, let's look at another problem. Let's say that I want to see how a person keeps their balance when they're standing upright. Now, this is still about modeling some dynamic behavior of the human body, but do we really need to model each single muscle? The answer is no. We can skip that part, and we can use a much simpler model of a double inverted pendulum, where the bottom link represents the legs and the upper link represents the torso. Now we care to know about the angles θ1 and θ2, and we can use Newton's laws, for example, to derive the differential equations. Again, we have to solve them first, of course. Now to something more interesting. Let's say that we want to model a man walking or running. We can use a similar approach. This time, we want to model each leg separately. So the leg that is not in contact with the ground, we want to model it as a normal double pendulum, not an inverted pendulum this time. And the leg that is in contact with the ground, we want to model it as a single inverted pendulum. So there you are. I just showed you a few examples of how you can use a simple system to simulate some more complex behaviors. Now, you might still wonder why modeling biomechanical systems is at all related to modeling engineered systems. Well, as a final note, I can only say that many engineered systems are designed to mimic biomechanical systems, and many other engineered systems are designed to interact with biomechanical systems. Human prosthetics, for example, they are designed to mimic the biomechanical system of an arm or a leg. Then you would need a detailed model of the arm of the leg or the leg so that you can build a system that has a similar dynamic behavior.